Sorry about that. The camera cut off on me and I only had about a minute or so to go. So maybe I'll go a couple extra minutes with my bonus time that we have here. But let's just see. I was saying that when we bring n into the situation and allow it to fluctuate, we could try to develop a similar equation to what we had up here for when n was constant. But sort of magically, no matter what gas we look at, if we multiply pressure times volume and divide by amount and temperature, we always get 0.08206 atmosphere liters per mole Kelvin, which is what we've come to call the ideal gas constant. Sometimes it's called the universal gas constant as well, but we'll use the ideal term here. And it negates then the need for having two different sets of equations because P1 V1 over N1 T1 just equals R now. And we can say, well, we don't need to worry that this is condition 1 just for any gas. It turns out then that PV equals nRT, if we just multiply the NT to the other side. And this is what we call the ideal gas law. It's a very powerful, effective gas law because it now lets us quantify gas samples in terms of their amount without actually weighing them, which is a problem we encounter in the lab. You know, in the lab, if you're working with a sample of sugar in a reaction, you can just weigh it. But if you have a sample of helium in a balloon, how are you going to weigh that? It's not even going to sit on the balance like a spoonful of sugar would, right? The helium's going to float up off the balance. But there still is mass inside that balloon. That mass is related to how many particles of helium there are. To know how many particles, you would need to know the other conditions of pressure, volume, and temperature. And so the gas laws allow us to quantify, and particularly the ideal gas law, allows us to quantify the amount of gas based on those other conditions, which we can measure in the laboratory. Pressure, volume, and temperature. They're a lot easier to measure. Now sometimes we can measure the amount of gas using mass, and when we can do that, if it's an unknown gas, that now becomes a way that we'll identify that unknown gas. Okay? But these are just a couple of the gas laws. Now if I return up here to this one collapses into a variety of other gas laws that you may or may not need. For example, if you hold constant the temperature in addition to the amount, the two temperatures are equal and they would cancel out in this equation, right? And you would have P1 V1 equals P2 V2, known as Boyle's law. Or if you held instead constant pressure, if the pressures were held constant for 2 trials of studying your gas, you would condense this to V1 over T1 equals V2 over T2. This was the gas law that led to the Kelvin scale, as it turns out. Just to give you some historical context as to why that was an important one. And lastly, the third variable, if we were to go ahead and hold volume constant, we would end up with P1 over T1 equals P2 over T2. And it's these latter two, although it was first discovered for volume, but both of these indicate the need for using the Kelvin scale, or an absolute scale, for when we study the temperature of gases. And so, as I said in the first segment, it's really important now that we always convert temperatures, even though we'll probably measure them in the lab in Celsius, that we immediately convert them over to the Kelvin scale so that gases are on that absolute temperature scale. All right? So I'll wrap it up there, and hopefully the next time you see me, we'll be in person in class, and we'll sort of pull everything together and start to work through some examples using these gas laws and putting them into some practical context for us. Thanks for your time again by watching the videos, and hopefully I'll see you soon.